Thank you for joining us as we embark on the exciting conclusion of our three-part, our trilogy of the method of undetermined coefficients. So what do we have left in store? Well, as always, leave it to math to always throw a little, wrench into the process, and to kind of give you an idea of what to look for as far as this wrench is concerned. Let's jump right into another example. So let's look at this example, and here's the differential equation. So it's y double prime minus 4y, and that's equal to 20e to the 2x, right? So again, on the surface, nothing really stands out. We do see that it's non-homogeneous, so we have to go through our process of finding, y sub c, y sub p. So let's go ahead and do that. So for y sub c, what are we going to do? We're going to solve the corresponding homogeneous equation, right? And that leads to this characteristic equation, m squared minus 4 is equal to 0. No problem there. Factors, it's a difference of two squares. So, hey, we're going to get our two real distinct roots. That's good. So, our m1 is negative 2, m2 is positive 2. If you wanted to write down, here's the basis for y sub c. So it's e to the negative 2x and then e to the 2x. So therefore our general solution, or I should say general solution of the homogeneous equation, or y sub c, is c1 e to the negative 2x plus c2 e to the 2x, right? So again, everything is straightforward. Let's move into y sub p. So for our particular solution now of the homogeneous equation, here's our differential operator, and we're trying to find what input, right? So again, if I think of this as my L of y, so what function, when I do these operations on them and combine them, will produce this sort of output, right? So here is our educated guess, right? So let's look at this guess. Well, we always see is a constant times a certain exponential function. That certainly fits our profile, right? So we're going to say, well, it's going to be some constant times e to the 2x, all right? So we know what we need to do in order to figure out what a is. We need to repeatedly differentiate this. So y sub p prime, that's 2a e to the 2x. Y sub p double prime, that's 4a e to the 2x. And what we want now is, so let's write down what L of y sub p is. So what does this differential operator do? It takes the second derivative, so 4a e to the 2x minus 4 times my original function. So a e to the 2x. So it's 4a e to the 2x, minus 4a e to the 2x. Well, this is always 0, right? So wait a second, but we don't want the 0 as an output. We want the 20 e to the 2x. So here is a problem. Well, what exactly caused this problem? And here is the root of this problem. Again, we're following our procedure, and based on, our f of x on this side of the differential equation, based on the output that we want from this operator, we made the standard guess. The problem is, though, look at the general solution of the homogeneous equation. Right? Essentially, look at the terms that make up the kernel of this differential operator. Any function of this form, right, a constant times e to the negative 2x, will always produce 0, right? Similarly, any function of the form a constant times e to the 2x, which is what we have here, will always produce 0. So that's what we're working with, right? So essentially, the problem lies in the fact that our educated guess duplicates, right? I'm just taking a term that's already here and maybe just blindly just looking at this part of the function, not even glancing back to look to see what are the elements of my kernel, and you realize that there's no way that a function of this form will give me this desired output, right? So what do we do? Is this the that dramatic moment in your the conclusion of our trifecta or trilogy? Well, here comes the hero, right? So this is the villain. So the fact that we have duplicate terms, that's a problem, right? However, there is a fix for this. So let me make a note of what the issue is. So what you want to look for, right? So when terms in our educated guess of y sub p duplicate terms, and doesn't have to be all of them, right? But some of the terms, at least one term. So terms in y sub c, our guess has to be modified, right? So our guess has to be modified. Now, there are several ways we can justify the process for modifying our guess. I am going to call your attention back to what we did when we had a repeated root. So when in case 2, when our auxiliary equation produced a single number, right? But we needed basically 2 functions. What did we do? We took, instead of duplicating like e to the 2x and then e to the 2x again, we took e to the 2x and we multiplied it by x. That's what we will use, that process, right? So that's my justification. I don't want to get into a super long justification as to why this modification process works, but think back to when we had repeated roots. That reduction of order process led us to a process of multiplying one solution by a power of x, right? In other words, x to the first power, to get the second linearly independent solution. So it's kind of along those lines. So here's our process. We modify our guess, whatever it is, in its entirety. So we modify y sub p by multiplying by multiplying our initial guess by the least positive integer power of x that removes all duplication. So that removes all duplication. So in other words, the first thing we're going to try to do is to multiply our guess by x. And if then none of the terms are duplicated, then that's what I will work, and the rest of the process will play out as expected. If after multiplying by x, I still have at least one duplicate term, I'm going to multiply by x squared. So in other words, you try x and multiply this. If that doesn't work, try x squared, multiply this. So you always go back to your initial guess. Another way to say it is you repeatedly multiply by x. In order to remove any duplicate terms. So based on this, here is our modified guess. I'll still call it y sub p, right? But what I'm going to do now is say, okay, this didn't work, right? I know it has to be basically something of this form, but it can't be this specific form because this form gets annihilated by my operator. I don't want it to be annihilated. I want it to give me what's the output that we want here? 20e to the 2x. So we're going to modify it by multiplying this by x. So it's basically x times a e to the 2x. So now putting it all together, I have this a x e to the 2x. And then what is always recommended, now go back and look at your kernel and see if any of the terms here, right, your kernel, your complementary function, your y sub c, whatever you want to call it, they're all the same. Look to see if any of these terms are identical to this in terms of the types of function here. Here I now have a to the x times e to the 2x. I don't have any term like that here in my in the terms of my kernel. So this is good to go. So let's see if now when we go through and find the first and second derivatives, if we end up with an expression that allows us to solve for a. See, the fact that this got annihilated, there was no way that I could figure out a, right? Let's see if now this can be solved. So again, go back and do our derivatives. Now, the thing about this process of modifying your guess is that since you're multiplying by powers of x, you automatically introduce the need for using the product rule. So there again, it's another instance where we're gonna have to do our product rule, but we can do it. Let's push on through. So treating the first function as ax and the second function as e to the 2x, I get this for my product rule. So a e to the 2x plus ax times 2e to the 2x. And again, I like the process of factoring out the exponential, just kind of keeping that e to the 2x as a separate factor. So the linear term now is a plus 2ax, and then that quantity is times e to the 2x. But we need our second derivative in order to completely apply the differential operator. So differentiate a second time. Derivative of the first function is 2a times the second. That's e to the 2x, and then plus the first. So a plus 2ax times derivative of the second, 2e to the 2x. Again, let's see if we can factor and group terms. So I have 2a here, and then distribute the 2. That gives me another 2a and 4ax, that entire quantity, times e to the 2x. So then I have some like terms, and let me write the inner part here. Let me write the linear expression in standard form. So it's 4ax plus 4a times e to the 2x. All right. So now that we have these, let's write down what our linear operator does. So L of y sub p of my modified guess, it takes the second derivative, which is 4ax plus 4a, that quantity, times e to the 2x, and it subtracts 4 times the original, so 4 times this. So I have minus 4 times ax e to the 2x, right? And the problem says that, well, the output has to be 20 e to the 2x, right? So that's what we want the output to be. So let's see if we can determine what a is. Well, here's what's cool, right? If I factor out the e again on this side, so this gives me a 4ax plus 4a and then a minus 4ax all times the e to the 2x, and that has to be identically 20 e to the 2x. But so notice what happens when I apply the operator, the terms that involve the x, they go away, right? Because I have 4ax minus 4ax, and then that leaves me with a really simple way of solving for a, because on the left hand side I have 4a e to the 2x. So this is the general form of what the operator will do to this type of input. And then I want it to be this specific output. So the only way this can be true is if 4a is equal to 20, therefore a is equal to 5. So we now got our particular solution of the nullity. So therefore y sub p is equal to 5x e to the 2x. Once I have this, still use the superposition principle. And here is our general solution. So the general solution is y equals y sub c plus y sub p, which in this case, so that was the C1. Let me just make sure that I'm using the form that I had earlier. Yep, so C1 e to the negative 2x plus C2 e to the 2x plus 5x e to the 2x, right? So you always want to look out for this issue now of, do I have duplicate terms? So now you know the potential for this problem to occur. What happens is, and let me illustrate it with a second example, and we'll go through it, and I'll just kind of point out, okay, this is where you'd look to see, do I have duplicate terms? And then you can just go ahead and modify it immediately instead of starting with a standard guess, running to an issue, and then having to go back. So it will save some time if you know what to look for mid-solution. And I think also for this example, let's go ahead. Now, so far, all the nullities that we've been solving, we were finding the general solution. But let's make this a full problem where we actually solve an initial value problem. So we're going to have lots of algebra to do, but I mean, algebra is fun. So let's say we're going to solve this. And now I could make it an initial problem or a boundary value problem. Let's go ahead and make it an initial value problem. That way we're going to be guaranteed to have a unique solution, right? So let's say we have this. Now, before we even start the process, remember, in order to utilize the initial conditions, you have to have a general solution of the differential equation first. So we're going to use these conditions, right, as we've done in the past, towards the very end. So we have to come up with the general solution, which is the y sub c plus the y sub p, before we can even think about using these conditions, right? So, and again, I'll highlight it once we get into the solution process. Okay, so first step, y sub c. So we have to solve the corresponding whole-d, right? So let's see, the auxiliary equation for this is m squared minus 2m equal to 0. So factor out an m, right? So we do get two real distinct roots. One's a constant, right? I'm sorry, they're both constants. One is 0 and the other one is 2, right? So So if you wanted to write down the basis for y sub c, it would be e to the 0x and e to the 2x, which obviously simplifies to 1 e to the 2x. So these are the two linearly independent functions. So our y sub c is c1 times 1 plus c2 times e to the 2x. So I'll just write it as a constant plus a constant times e to the 2x. All right. So now let's see. The right-hand side, it's again simple enough. We have this is a first degree polynomial. So our guess, right? So for y sub p, right, so this is our guess. So we're gonna guess that y sub p, well, following our pattern, it should be another first degree polynomial. So I'll have ax plus b. But, and it's nice to have this right here, here lies the problem. An element of the kernel is a constant. My y sub p has a constant term. So this term will always be eliminated by this linear operator. So I will never, so think about what that means. If this term is always going to be eliminated by this linear operator, then I will never be able to solve for this. In other words, it will always vanish. So I'll never be able to set up an equation that will have a b in it that allows me to solve for b. The reason why is because of these. These are duplicate terms. All right, so this is what we can look for, right? We can look for it and say, okay, no, my kernel already involves just constant terms. So constant terms and constant times e to the 2x terms. Any function on the right-hand side, right, that would have something like this and or something like this would lead us to modifying our guess, right? So duplicate terms. So let's modify our guess. So modified guess y sub p. So what do? We take everything that we have here because it has the it has the right spirit, right? It's in the right ballpark, but not quite specific enough. So we take the ax plus b, apply our modification process, and multiply by x. So if I have, so x times the quantity ax plus b. So this is now going to be my guess. This is what I'm going to work with. Ax squared plus bx, right? And again, when you kind of look at this, notice we're not right. It's not even that we're writing down like a general quadratic. No, we're just saying that it's our modified guess is something linear times x, right? So we don't have like, I think in general what would happen is if you put a plus c there, the c would end up being 0, right? In other words, it was a term that was unnecessary to begin with. So you would probably end up giving yourself more algebra to do if you include terms that you don't. But what you want to do is to make sure that your guess, when you look back at what we've written down here, there is no ax squared term in our kernel. There is no constant times x term in our kernel, so we're good to go. So based on this, we should be able to identify a and b. And then, so in order to do that, we need the first and second derivatives. Since it's a polynomial, it shouldn't be too bad. So y prime is 2ax plus b. Yp double prime, that's 2a, right? And then let's set it up. So our operator when applied to our modified guess, so this function, it takes the second derivative, this operator takes the second derivative and subtracts 2 times the first derivative. And notice now we still have a b in there. So that's going to give us a way of solving for b. So 2ax plus b. And we want that to be identically, so our function on the right is 3x plus 4. All right. So let's go ahead and let's simplify the left-hand side. In other words, the general output. And so we have, okay, so negative 4ax, and then 2a, and then minus 2b. So I'm just kind of writing it in that standard linear form, and then we can compare it to the linear form of the output that's desired. And what this means is this coefficient of x on this side has to be equal to this coefficient of x on the right-hand side. So these two have to be equal, and then the constant terms have to be equal. All right, so therefore negative 4a is equal to 3, so a is negative 3/4. And the other equation, 2a minus 2b, that has to be equal to 4. So if I plug negative 3/4 in here, I'll have negative 3/2 minus 2b is equal to 4. So negative 2b is equal to 11/2, and then divided by negative 2, so b is negative 11/4. So putting this all together, my y sub p is equal to, it's the a, so negative 3/4 x squared. This goes back into my modified guess, and then minus 11 over 4x. So now let's put the general solution together. So the general solution is y equals, so y sub c, let's go back up, take a look at it. It is c1 plus c2 e to the 2x. Right, so c1 plus c2 times e to the 2x. Now add this particular function together, and voila, our superposition principle is in play. Right, so this is a general solution, but now we have conditions. So it's based on this that we find C1 and C2. So we don't find C1 and C2 mid-solution and then find the particular. No, because the particular solution function may impact C1 and C2. We don't know, right? You find the general before you find the particular solution. So our first condition is y of 0 is equal to 4. And then the second condition is y prime of 0 is equal to negative 3. So since we're going to need y prime, let's go ahead and differentiate our general solution. Once we do that, c1 goes away. When I differentiate this term, I'll get 2c2 e to the 2x. When I differentiate this term, I'll get negative 3/2 x. When I differentiate this term, negative 11/4, right? So now let's apply our conditions. So when x is equal to 0, y is equal to 4. So what do we get there? So I have c1. X is equal to 0, so I end up with e to the 0, so that's 1. So I have c2. Both of these terms involve x, so they both get eliminated. So I have that is c1 plus c2 is equal to 4. The next condition, it says when x is equal to 0, y prime is -3. So that gives me, so let me write down this side first. So what's nice is I'm not going to be, I'm going to know exactly what C2 is, and then it's going to make it easy for me to find C1. So I have 2C2 times 1, so 2C2 minus 0 when I plug x equals 0 here, and then minus 11 fourths. That has to be equal to -3. So add 11 fourths to both sides, and you will get, what's that? Negative. Okay, so we have 2C2 is equal to, so this is -12 fourths plus 11 fourths. So -1/4 divide by 2, so C2 is -1/8, right? That's good. And then what is C2? Well, sorry, what's C1? So C1 is equal to 4 plus 1/8, which is 33/8. So 33/8. And there we go. So here is the particular solution, or the solution to the IVP, the particular solution to the IVP is y equals, so C1 is the 33/8 plus C2. C2 is -1/8. So let's write that as -1/8 e to the 2x, and then minus 3/4 x squared minus 11/4 x, right? So this example shows us the full process now. When we have a pair of conditions, in this case we had initial conditions, we first find our general solution using our y sub c and y sub p, and then based on that, get our equations to solve for our C1 and C2 constants, right? So there we go. And that ends, right? That is now the conclusion of our trilogy of the method of undetermined coefficients, right? So I don't know which part of the trilogy you think was the best. You know, usually they say the sequels never compare to the original. I don't know. I'll leave it up to you. I thought there were intriguing moments in all three of them. And for more mathematical intrigue, I'll see you in the next video.